What if there was a cost-efficient and more profitable manufacturing process that allows designers and engineers to utilize sculptured aluminum panels that are structural as well as ornamental? That revolutionizes the bridge building industry by replacing high-maintenance steel components with more affordable and efficient materials of lower maintenance requirements. That reduces construction time and lowers costs for mass transportation tunnels made of large structural panels, and makes possible the net shape forming of large aerospace parts for both military and commercial applications. Well, the future is here. Introducing the next generation in metals manufacturing technology, pull form, a proven process that can fabricate components faster than machining, more accurate than conventional forging, and still maintain lower costs. The pull form process squeezes material in a progressive and sequential motion that gradually compresses material to completely fill a female die cavity of a desired shape. A pull form die consists of a lower female half and an upper male half. The male portion is made up of segments where each segment can move independent of each other. The pull form process fabricates structural parts with minimum material waste, less flow time, and enhances the structural integrity of net-shaped parts. Pull form technology created this part, weighing 0.95 pounds, from a blank weighing only 1.06 pounds, resulting in 3.8% scrap. If this same part were machined from thick plate stock, 5.12 pounds of material is required, resulting in 81.4% scrap. Starting with equal weights of stock material, machining produces one part and a large volume of scrap. The pull form process produces 4 parts and a small amount of scrap produced as flash. The pull form process is more rapid and more material efficient when compared to machining. Conventional machining produces over 26 million tons of scrap each year. The production of a typical aircraft part using the pull form process begins by placing an aluminum blank coated with lubricant into the female die cavity. For parts with flanges on one side, a steel cover plate is positioned over the aluminum blank. The male segments are then positioned in place within the female portion of the die. The die assembly is placed in a furnace and heated to a predetermined temperature. The pull form process has made prototype subscale parts from aluminum, lithium aluminum, and metal matrix composites. The pull form process can also be used to shape titanium and titanium matrices. Upon reaching the desired temperature, the die assembly is moved from the furnace and secured to a hydraulic cylinder. As the male segments come in contact with the inclined surface, each segment is gradually forced down, shaping the heated material to conform to the contour of the female cavity. The hydraulic cylinder pulls the die assembly, encased in a die holder, past the inclined surface at a rate that is suitable for the material being formed. After the forming process, the male segments are gradually raised from the female cavity by an extraction ramp. At the extraction station, hydraulic pressure is used to eject the finished part. The black coating on the part is the high-temperature lubricant required to reduce friction between the aluminum being formed and the steel die surface. After removal of flash and surface lubricant, the finished part is net shaped and has an RMS surface of 32, with no surface machine marks. The many types of aluminum formed with pull form so far have been pulled at rates varying from 6 to 10 inches per minute. This part, which is 11 inches long, requires approximately 2 minutes to pull form. This production part, made at a leading manufacturer, required 20 hours of machining and 4 hours of hand finishing. If produced in a production pull form system, it is estimated that 4 hours would be required. The actual shaping in the pull form system would take only 30 minutes. Cutter marks on machine parts require hand finishing, and if not properly performed, can attribute to premature component failure. Minimizing the use and maintenance of cutters, along with the expense and control of lubricants and cooling fluids, will lower costs and improve productivity. When compared to machining and conventional forging, pull form is a significant move toward automation and improved producibility.
Let's look at a wood model of a production-type flow-forged machine. The process is so rapid, it can keep several furnaces busy heating dies and material. The major difference between this model and the prototype is that the compression sidewalls are equipped with indexing holes. To avoid the expense and limitation of using a fixed large cylinder with a long stroke, a system of indexing holes in the side plates allows for a shorter cylinder to index back and forth as required. A standard cylinder with a short stroke can be used to forge parts of any length. Movable furnaces are included as part of the system to effectively move large dies quickly and easily between the furnace and the inclined plane. All of the force required in shaping the material is performed at the inclined plane, and the power needed is only a fraction of that required by conventional forging equipment. In addition, the localization of pressure in this sequential manner results in improved material flow and excellent filling of.
The result of the pull form process has been demonstrated on this prototype equipment. The results are rapid, repeatable, and offers capabilities not available in existing processes. Now, in addition to the material and labor savings you see here, engineers and designers can focus on increased physical properties, especially improved resistance to premature failure due to fatigue. We feel that in time, the pull form process will gradually replace a significant portion of machining and conventional forging operations. We believe in moving material, not removing.
The FlowForge team that developed this new technology has demonstrated the feasibility of fabricating parts without making chips. Future savings in material and labor will be realized when FlowForge is in production moving, not removing metal.